Hey guys, I'm Jay. Today is my LeetCode review one-take vlog on 103rd problem. Binary tree zigzag level order traversal. We are given the root of a binary tree. We'll return the zigzag level order traversal of its node's value, i.e. from left to right, then right to left, for the next level and alternate between. Let's see example 1 here to understand this problem easily. We got the empty binary tree here, and our output should be 3 in the first layer, and 20 and 9 in the second layer, and 15 and 7 in the third layer. Then, let's get started with our intuition to solve the problem. And there are 2 key points. First, we can use breadth first search or depth first search to traverse the whole binary tree. And the second key point is alternate the direction of traversal. At each level, we need to change the direction of traversal. For odd levels, we process from left to right, and for even levels, we process from right to left. Alternate directions for each level. Then let's get started with the first approach, breadth first search. So at the beginning, we'll create a list to store each list at each level. List of integer. Let's call it result list. We'll initialize a new empty array list for the result variable, new array list. Then we'll handle a bad case. If the root node is null, then we just return an empty list because there are no nodes to traverse. So if root equals null, we just return the empty result list. Next, we'll initialize a queue and add a root node into it. We'll use the queue to help us keep track of nodes to be processed at each level. The code is queue of tree node. Let's call it queue, and we create a linked list instance to the queue variable, linked list. Then we'll call the offer method with the root node, queue.offer of root. Next, we'll create a flag to toggle the direction of traversal for each level of the binary tree. Boolean with left to right flag. And we'll initialize the variable as true for the root node, which is the first level. And then we'll implement a while loop to traverse each level of the binary tree. While. Now symbol with queue dot is empty. If the queue is not empty, we'll keep the while loop. And inside the while loop, first, we have to determine the number of nodes at this level. So the code is level size equals queue.size. Then we'll create an extra array list to store all the nodes in this level. A list of integer. Let's call it list. We assign a new empty array list to it. Then we implement another for loop to traverse each node at this level. Integer I started at 0. I should be less than level size and increment I after each iteration. And inside the for loop, first we'll pull a tree node from the queue. Tree node, let's call it tree node, equals queue.pull. Then we'll add the current node's value to the front or the end of the array list for this level. And it is according to the left to right flag. If left to right flag is true, we'll add the value into the end. So the code is list add with tree node dot value. On the other hand, if the left to right flag is false, we'll add value into the front of the list. List dot add, the index is 0 and tree node dot value. Then we'll add the subtree to the queue for the next iteration. If tree node dot left is not equal to null, then we'll add the left subtree into the queue.offer with tree node dot left. And if tree node dot right is not equal to null, we'll also add the right subtree into the queue for the next iteration. Queue.offer with tree node dot right. And that's all the code inside for loop. And out of the for loop, then we need to alternate the direction for the next level. So the code is left to right flag is assigned to a new value with a not symbol, left to right. Then we'll add the current levels list into the result list. So the code is result list.add with the list. And out of the while loop, then we just return the result list as the problem asks for. Let's submit code and check for correctness. Then let's analyze the time and space complexity. Yes, our code got accepted. So the time complexity, it is big O of n, because each tree node in a binary tree is visited only once, and each operation, inserting a node's value or adding children to the queue, takes only constant time. So the overall time complexity, it is big O of n, and n is the number of nodes in the tree. And the space complexity is big O of n too, because the queue that stores the nodes at each level, and in the worst case, the queue would contain all the nodes in the bottom level, which is half of n. And this situation could be approximately n divided by 2 nodes. So the space complexity remains big O of n. Then let's get into the second approach, which is the depth first search. Let me clean the code and then start it with the second approach, depth first search. First, we still have to create a new empty list to store all the node lists for each level. So the code is list of integer. Let's call it result list. We assign a new empty array list to this variable. Then we have to call a recursive method. Let's call it depth first search, and this method could take 3 variables. And the first variable is the current node. And for this situation, we'll pass the root node. And the second parameter is the depth. So we pass 0. And for the final one, we just pass the result list. So we can store each list at each level. And for the final part, we just return the result list. Next, we have to declare and implement the DFS method. First, the method is private and has no return value. And the name of it is DFS, and it has 3 parameters. First is the current tree node, let's call it node, and the second is the depth, and the final one is the result list, integer with result. And inside the method body, first we still have to handle the bad case. If node equals null, we just return. And then we have to check if the current depth level exists in the result list or not. If not, we'll add it to store elements in this level. If result.size is less than or equal to the depth, which means we have to go into a new level. So we have to create a new array list to store all the nodes in this level. So the code is result.add with new empty array list. And then we have to insert the tree node value in the appropriate order based on the depth. If the depth mod 2 equals 0, then we'll add the node's value into the end of the list. The code is result.get with depth, and we'll add a node value, node.value. And on the other hand, we'll add a node's value into the front of the list, result.get with depth, and we'll add the node's value into the front of the list, which is the index 0, node.value. Next, we'll recursively process the left and right subtree if these subtrees exist. So we'll recursively call the DFS with 3 parameters. First is the root node of the left subtree. So the code is node.left and the new depth. So we'll increment depth with 1. And the final one is the result list. And we have to do the similar action for the right subtree, which is node.right. And that's all of the code for the second approach. Let's stop in the code and analyze the time and space complexity. Yes, our second approach got accepted. So the time complexity is still big O of n, as we visit each node only one time, and each insertion operation takes constant time, which is big O of n. So the overall time complexity, it is big O of n, and n is the number of nodes in the tree. And the space complexity is big O of h. H stands for the height of the binary tree due to the recursion stack. And in the worst case, if the tree is a skewed tree. So h could be n is the number of nodes, and in the best case, if the tree is a balanced tree, so h could be log of n. So h is between log of n to n. And that's all the code, and that's all for this problem. And I highly recommend you guys to visit my online GitHub page here. You can see all the problem description, intuition, an idea, and codes with detailed comments, and final time and space complexity analysis. You can also visit my GitHub repository here, which contains all the code and nodes to build this online GitHub page. And I'll put those two links on my YouTube description below. And thank you guys for watching. I'll see you next time. Bye bye.